Analytical Chemistry 1, Lesson 7. Return now to the nitrite analysis. We need to make up the diluted solutions so that they can be used to calibrate our instrument throughout the range of concentrations we anticipate to encounter as unknowns. We start with the stock solution we made up last lesson. It is 48.9 ppm in nitrite ion, as well as being 73.4 ppm in sodium nitrite. All of the calibration solutions will be drawn from this solution. Therefore, the accuracy of your calibration depends upon the accuracy of the solution. Did you dry the material correctly? Did you weigh it correctly? Did you transfer it completely and without contamination? Did you fill the volumetric flask correctly? Did you properly mix the solution so that the solution was uniform? You must get all of these steps right before proceeding. Now we need to create a series of solutions between 0.5 and 20 ppm. Question for you. Do we need a solution that is exactly 0.50 ppm and another that is exactly 20.00 ppm? Hopefully you can again appreciate that we want a series of solutions in this range. They need to have concentrations that we measure accurately, but they do not have to be a nice round number. The volume we will need depends upon how they are to be used. We'll only need a few mils of each solution to run the calibration experiment, so let's work with 25 milliliter volumetric flasks. As an example, how would we make up the 10 ppm solution? Our stock solution is 48.9 ppm, so we want a dilution of about 48.9 over 10, which is about 4.9. So a final volume of 25 milliliters would require putting in about 25 over 4.9 or 5.1 milliliters. How do you obtain this volume? Well, graduated pipettes have markings on them to be able to deliver readily solutions with 0.05 milliliter precision. More sophisticated micropipettes and electronic pipettes are increasingly available to deliver these volumes accurately. Let's assume that you have extracted 5.05 milliliters from the stock solution and transferred it to the 25 milliliter volumetric flask. Fill the flask to the mark with your pure water. What is the final concentration? Well, the feature that is common before and after dilution is the amount of nitrite. Concentration times volume give moles of substance. This gives us the well-known dilution relationship C1V1 equals C2V2. This is just saying that moles of nitrite before dilution is the same as that after. With this, we see that the concentration of the diluted solution is 48.9 times 5.05 over 25.00, or 9.88 ppm. We would follow this procedure, say 7 times, for concentrations that cover the target range. We would then have 7 solutions between 0.5 ppm and 20 ppm. We run each of these 3 times through the HPLC-MS, which provides an integration of the peak area for the nitrite. A number with arbitrary units is given as the magnitude of the response. A good instrument will provide a linear signal in this range. That is to say that if you graph the signal against concentration, it produces a nice straight line. To get reliable results, you would recalibrate the instrument daily, weekly, or monthly, depending on your experience with its stability dictates. Then any unknown sample provides a signal you can use, and you can use this calibration curve to determine the concentration. If your unknown concentrations lie outside this range, you need to extend the calibration range to ensure accuracy. Extrapolating beyond the calibration range is seldom a good idea. As an example, here is a possible graph of the signal for 7 concentrations over this target range. I've plotted these in Excel. I've used Excel to plot the best fit straight line through these data, and it then provides the equation of that line. In this case, it is y equals 8.7398x plus 3.2637. The y-axis graphs the signal from the mass spectrometer. The actual number will depend on a variety of electronic settings and numerical procedures with the data. That is why I have described the output signal as arbitrary. But once those are optimized and set, the signal is very reproducible. The x-axis is for the nitrite concentration. The equation looks like this. And you can now use this calibration curve by inverting the equation to solve for the nitrite concentration. So you'll take a small sample of water from your aquarium and inject it into the HPLC. A little over a minute later, you get a result from the mass spec for a signal of, let's say, 39.28. Use the inverted equation to find that the concentration is 4.12 ppm. You can inspect the graph by following the red line. This is basically what the inverted equation does, and you can see that a number around 4 ppm is to be expected. You might conclude that your aquarium is working well and the fish are not at risk. Hopefully you have a very large exotic fish business to warrant spending $500,000 on the HPLC-MS system. One more word about significant figures. When you weighed the sodium nitrite, it needed to be in something, a glass vial, a plastic weighing boat, or on a weighing paper. But that something weighed something too, so you needed to have weighed the container. First by itself, and then again with the powder, and finding the difference to determine the mass of powder. For example, you might have a container that weighed 22.5792 grams, and then you added the sodium nitrate and reweighed it, finding a value of 22.6526 grams. Subtract the two, and you have the 0.0734 grams of sodium nitrite that was then added to the 1 liter volumetric flask. The two weighings produced numbers that had 6 significant digits in them. Why did the number we end up using, the concentration of 73.4 ppm, only have 3? Well, let's remind ourselves about significant digits, which are the minimum number of digits required in reporting a number without any loss of accuracy. Some confusion arises around the use of the number 0. Sometimes it is a significant digit, other times it is just there to help define a decimal place and does not contribute to the accuracy of the number, just its magnitude. The number 22.5792 has 6 significant digits. The number 0.0734 has only 3 significant digits. The leading zeros just help to define the magnitude. The weight of sodium nitrite is 0.0734 grams, or also 73.4 milligrams. Both numbers have 3 significant digits. We just shifted the decimal place around and used prefix multipliers in scaling them. The accuracy of both numbers is not in question. Now, what if the second weighing produced the number 22.6522 grams? Then the difference would be 0.0730 grams. Is that last zero significant or not? Well, we compare 0.073 and 0.0730 when we write these numbers. In the one case, we are implying that we know that it is not 0.072 nor 0.074, while in the other case, we are saying that we know it is not 0.0729 nor is it 0.0731. Clearly, the first statement implies a much larger range of possible numbers. 0.073 is less accurate than 0.0730. The precision of the analytical balance implies that we have weighed something to 0.0730 grams. The last zero is significant. So here are the rules for significant figures involving 0. Zeros inside a number are significant. 75.304 has 5 significant digits. Zeros to the left of a number are not significant. 75.304 still has only 5 significant digits. 0.0075304 also only has 5 significant digits. Zeros to the right of a number are significant unless there's no decimal place given. 75.30400 has 7 significant digits. 75.30400 is ambiguous. It's not clear if these last two zeros are significant or not. However, 75.30400.0 has 8 significant digits. Writing a number in scientific notation is always the best for clarity. 7.5304 times 10 to the 6 has 5 significant digits. 7.53040 times 10 to the 6 has 6 significant digits. 7.530400 has times 10 to the 6 has 7 significant digits. In an alternate approach, some people will argue that 7530400 point indicates 7 significant digits. Notice how we have just added the decimal point. Note how that is different from 7530400.0, which has higher precision. The first is claiming a difference between 7530401 and 7530399, while the second is differentiating between 7530400.1 and 7530399.9. The next question that always arises is how to carry significant digits through various mathematical operations. This is the answer to why the balance weighed 6 significant digits, but the weight of sodium nitrite was only found to have 3 significant digits. Addition and subtraction first. Well, the answer is taken to the least significant position amongst the numbers involved in the operation. The answer can have more or less significant digits than any of the participant numbers. This is just what happened with the weighing of the sodium nitrite. We subtracted 2 numbers with 6 significant digits from each other and end up with a number with only 3 significant digits. But all 3 numbers involved had their least significant digit in the 4th decimal place. By contrast, look at this addition process. We add 2 numbers, each with 4 significant digits, and obtain an answer with 5 significant digits. Well, that's just what happens. When you are presented with numbers written in scientific notation, Convert them so that they are all written to the same power, or convert them all to their floating point numbers. But if the exponents are large, positive or negative numbers, that might be difficult. But get them all to the same power. Align the decimal position and add them together. The answer is rounded off to the same number of decimal places as in the number with the fewest. And note that it doesn't matter which exponent you adjust them to, just as long as they are all the same, it leads to the same answer. Now, multiplication and division. The answer is expressed with the same number of significant digits as is found in the number which has the least number of significant digits. When multiplying two numbers, we look for the number with the least number of significant digits and then round the answer to that many digits. In some cases, it can lead to numbers that seem to have too few digits, but it is the right thing to do. Another situation can arise when rounding leaves you with trailing zeros. In this case, the number 3600 is ambiguous. Another reader might think you intend that there is only two significant digits. You could put a decimal after the last zero, but I think it is even more clear to use significant scientific notation. There are 4 significant digits in this answer. There are numbers that are not measured, and the concept of significant digits doesn't really apply. These are the fixed constants that often appear in equations. Kinetic energy is 1/2 mv squared. The 1/2 does not contribute to the discussion of the answer's number of significant digits. Just as 2 pi's digits are controlled by how many we want to use from pi, not from the number 2. And logarithms and exponentials. You must understand the difference between the character and the mantissa of a logarithm. The character is the numbers before the decimal place, to its left, and the mantissa is the numbers after the decimal place, to its right. The character is related to the exponent in scientific notation. It adjusts the decimal place, but not the precision of the number. The mantissa dictates the precision. It is sometimes called the significand. It is the part that determines the significant digits. The mantissa has as many significant digits as the original number. And we see the same thing in scientific notation. Chemists encounter logarithms and exponentials both in base 10 and in base e, use the same logic in both cases. To justify this choice for significant digits, look at the number 4628.3, which has 5 sig digits. We would report its base 10 logarithm as 3.66542. Look what we get when we exponentiate this value and compare it with what we get when we change the last digit by 1. First, we exponentiate the base 10 log, and when rounded to 5 sig digits, we get back the original number. We change the last digit by 1, and when rounded, we get 1 less in the answer. Same thing happens when we increase the last digit by 1. The correctly rounded result has 1 more in the last digit. You must see now that when you exponentiate a number, retain as many significant digits in the result as there are digits following the decimal point of the exponent. And in counting digits, include even the leading zeros in this case. For logarithms and exponentials, this focus on the portion after the decimal place, the mantissa, certainly seems to be warranted. If you ever want to check these things, try changing the last digit of your operand by 1 and see where the changes in the result come. And in this way, you can start to see where the idea of significance comes from. Just a final reminder about calculations and significant digits. Numbers are rounded off to the correct number of significant digits at the end of any long multi-step calculation. You do not round off intermediate results. This can lead to the accumulation of errors along the way. Know the significant digits in the numbers you start with. Watch for the type of calculations along the way and round the final answer appropriately. Throughout the calculation, carry through several additional digits beyond the ones of significance and only round off right at the end. In this example, the multiplication by 7.87 ends up killing off many significant figures in the exponentiation. Think what happens if you were to multiply instead by 0.787 or 0.0787. How would that change things?